All right, so we're going to kind of continue our discussion on filter structures. And last time we talked about linear phase FIR filters and kind of some redundancy that comes out of those filter coefficients. We got to kind of tie up a few loose ends on IIR filters on this segment. And we've already run into most of these concepts in our lab work, so I'm not going to spend a whole lot of time talking about it. When we talk about numerical stability on IIR filters, there's a ton of work, and there's actually a pretty good segment in your book about how to model rounding errors, and particularly if you're dealing with integer math, it becomes a huge issue to make sure that filters are numerically stable. Numerical stability problems end up being more important for the IIR filters than the FIR filter cases. The FIR filter cases can never go unstable, but everything we do here really applies to either the IIR or the FIR case. More common, we're going to deal with it for the IIR case. So if I have a high order filter, and who knows what we mean by high, but if I have a high order filter, almost always to get around the numerical problems, I'm going to do a first step where I decompose this thing into lower order filters. And so that means I'm going to use several low order filters. And in kind of the most common cases, the one we used in the lab, we can talk about cascade implementations. Second order filters. And so every filter you've ended up implementing in the IR form in our lab has been, we've forced you right from the start to use these cascaded implementations where I break H of Z down into smaller order filters. So the scheme to get to a cascaded second order filter, set of second order filters, set of biquads, is I'm just going to factor H of Z, right, into a lower order polynomial. So if I have B0 Z to the minus 1, and so on out to B sub n Z to the minus m, denominator polynomial A0 plus A1 Z to the minus 1, and so on, A n Z to the minus n. Turns out, if I start looking at rounding error on these, the frequency response of this filter depends on the location of the poles and the zeros, the roots of these polynomials, right? And you've done in your lab where you were hand placing roots, and that tends to be pretty sensitive. It doesn't take much of a change in the location of the roots in order to make a big change in your transfer function, particularly when you talk about poles that are out near the unit circle. Moving it just a small amount can make many dB difference in the gain of the filter, or it can make it go unstable if we move across the unit circle. Turns out directly using these coefficients in a direct form for a high order filter is almost always a mistake, right? And the tiny rounding errors in the polynomial coefficients can make big differences in where the roots lie on the complex plane, and big differences in your overall transfer function. So to get around that, instead of dealing with high order polynomials, we like dealing with lower order polynomials. And so I'm going to take that transfer function, and every conjugate pair I'm going to group together to get second order transfer functions. I'm going to end up with a product. I'll use a capital pi to represent the product, so as I'm multiplying all these guys together. Little k going from that to a bunch of low order transfer functions. Okay, and normally these things are second order. Okay, so if I can factor this thing into its roots and then group the complex pairs together so I get nothing higher than second order transfer functions, then I'm way ahead of the game even to start with, because my polynomial orders aren't that high, and the rounding errors, the movement between the coefficients and the roots is much more controlled for second order than it will be for, say, a 10th or 15th or 16th order filter. Okay? So we'll almost always take that step, and we force you to take that step in every lab you've ever done in here. So the overall implementation is this cascaded version where I have a whole bunch of filters. Instead of trying to build one complicated difference equation for the high order filter, I'm going to use 2 poles and 2 zeros down here, 2 more, and so on, right, in order to get to the overall collection of poles and zeros I want. Okay. Every pole I'm going to keep with its conjugate, every zero I'm going to keep with its conjugate, and I do that so that the coefficients in these polynomials are all real. Okay. Each one of these things has a transfer function h of z that's second order, b0 plus b1 z to the minus 1 plus b2 z to the minus 2. Okay, so there's my generic second order transfer function. Usually when I'm dealing with rounding errors, our starting assumption is that we've already taken that step, and for 9 times out of 10, that's enough to get around many of the rounding errors that you can have, at least for a floating point processor, not necessarily for an integer processor. When people start looking at rounding errors for filter implementations, we spend a lot of time concentrating just on second order filters, right? Because if I can get a filter structure that's well behaved for the second order case, I can get a filter structure that's well behaved for higher order cases. Okay, and we've already seen different implementations of the second order filters. You should already know about the direct forms, 1 or 2, right? So those we've kind of beat into the ground. Another one you run into from time to time, and actually if you've used the built-in routines on the ST libraries, you've seen the transposed direct form 2. And that one's pretty common, right? It has some advantages for some processor architectures. So let me draw a block diagram of that one just so you've seen it once. So this is x of n coming into the filter. I scale on a feed forward path, B0, B1, B2, and then this here, this is actually a summing block. My signal flow goes in the opposite direction for this filter, so I'm going to, in each case, do a sum and then feed to delay that goes into the next sum, right? Okay, and this should be a sum again. And then on the other side, I bring in my A2 minus A1, and this ends up being my output sample. Okay, so my current output is fed back into each of these, and so here's really a different structure, yet another different structure, where it's not all obvious just looking at that's going to have the same difference equation, the same transfer function as what we started with up here. But if we go through the work and write down the delays and how things are added up, it turns out x of n and y of n are governed by exactly that same difference equation that we're used to seeing. There are many other second order implementations. If you run into a numerical problem, it's worth your time to go into the book and start seeing different structures. And a lot of the most numerically stable don't involve these polynomial coefficients in the filter structure at all. We round things off to make things a little bit better behaved. Okay. Cascade implementations aren't the only option. You can do a parallel implementations. Parallel forms. And depending on, if I have a parallel processor, it might be a pretty attractive thing to try to do. And there what I'm going to do is I'm going to take h of z and I'm going to rewrite it as a partial fraction expansion. So I might have a constant, and then I have a sum of a whole bunch of terms that are, I think in our normal partial fraction expansions, they're just first order z minus p sub k, right? Okay. But I might have second order terms in there as well. Pretty simple idea here is if I can get a partial fraction expansion, that means I can implement this filter by using a whole lot of low order filters in parallel. X of n just sculled by a factor of c. I'm going to filter by the first stage here, and then I just add up all my filter outputs filter the same input by a second stage, and so on. So I put each of these guys in one of these filter stages. If I want real coefficients, I'm going to take whatever one I have in here and combine it with its conjugate to put a second order filter down in this parallel implementation. But my overall transfer function is the sum of the outputs of all of those filters, right? So simple idea, works well. Has some computational efficiencies if I can offload these calculations among different processors. And some disadvantages, so the cascade representations tend to be much more common, particularly where I'm talking about a filter that's selecting a band of frequencies. If I'm trying to reject frequencies that are not desired, these zeros end up being important. And if I can get the zeros right in any given filter, I'm guaranteed they're going to be implemented correctly. You know, if a given frequency is blocked in this filter, it's blocked from here to here. On the other hand, zeros are tricky to control with the parallel structure. You have to have some perfect cancellation between all of these stages in order to implement a zero. So zeros tend to be a little less stable for the parallel implementations. So the cascade ones are probably more common. Rounding errors are tough. They're nonlinear problems to examine. A couple of techniques here that are almost standard, that are almost always used to avoid the rounding errors. Your book has a great little section on how the poles might move as coefficients are rounded, and it ends up being very important for integer processors, which are not at all uncommon. But I think that's about as much as we're going to say about that topic. So I'll break there.